Okay, in this video I'll do a brief introduction to summation operator that will be useful in your statistics or econometrics courses. Let's look at the simplest case of some where you will be using summation operator. Let's say, well, let's start with writing what it is actually. So it's a sigma sign from Greek alphabet. You usually have indexing operator here, starting, let's say J, I, could be N, could be any letter. Usually we use the Latin alphabet here, while that sigma itself is from Greek alphabet. J usually starts from some number, could be 0, could be 1, could be any number. Let's start from 1 as the case usually, and then here this is the starting value index, and at the top of the sigma sign you will put the final value, J equal to some let's say capital letter N. So this is the last observation in the array of numbers that we are summing up. Now instead of N you could have as infinity sign here to imply that the summation runs to infinity. That I will leave it for another case. So this is the simplest case here with the observations in front of the sigma sign, to the right of the sigma sign. So this is J. So it is important that we have the J's here because indexing is governed by J, letter J. If you have I, then summation operator treats this expression here as a constant, so it won't be summing up across I's, it will only be summing up across J's. Right, so as you know from your first year courses, this expression boils down to this little bit longer, not so beautiful expression. So J starting from 1, so this will be x1 then, and a first observation in the list, let's say of n observations, plus x2 plus x3 plus, and then you have all this intermediate summations x n minus 1. It could be a capital letter N here or a small letter n, small caps as well, plus last observation n. Now yeah, this is simple and this is something you've done before, and this is the simple algebraic expression summation, while this is more more often you will see this operator in statistics and this year in econometrics too. Now let's look at cases where it gets a bit confusing. Let's look at this case where you have summation over J equal to 1 to n, and now I'll make it easier for myself. Rather than saying J equal to n, I'll just put n here. I could actually do this as well if I want to. I could instead write just 1 to n to make notational simplifies, but let's keep it as in the books, right? So if you have this sort of expression where x's are squared, what we'll do in this case, and then there's another case where, so I'll just make it a bit complicated in this case. I thought I will do it later, but let's look at this case as well. These are quite often encountered in proofs, in formulas of statistics. Now these two expressions are totally different. They imply something different, and I guess you know what they are, but let's look at what they are in case you don't know. So if this case tells us it's the sum of the squares of observations, so this will be x1 running from 1 squared plus x2 squared plus x3 squared plus, well, we have the intermediate points here, which I will just leave it to you to look at. Well, you don't need to look at, obviously. So this is what it is basically, a sum of squares of x. Now in this situation, in this case, we have to have the big bracket here, x1 plus, so this is actually square of the sums. So these are the three, well, not three, two cases where it might be a bit confusing, but I guess it won't be for you. We've done it before, and it's some sort of refreshment for you, right? So what else here? just to start. Okay, these are basic rules of summation. Now let's look at the case where constant is involved in our summation operator, and let's name it first rule of constant. So, and I'll just clean it. So let's say first rule of constant in summation notations. Let's say we have this case where j runs from 1 to n again with some a. So you might come across this case. In that case, what we do? Well, a is not indexed by j, so we won't be adding all j's in this case. But what we do is, since there are n points that runs from j1 to n, we'll add n a's. So a doesn't change from j to j. So from observation to observation, a will stand constant. It's a constant, it's not observed. So there are n of these, means n times a. Or in the simplest case, you would simply look at the last observation or last number in the indexing and times it by a. So if this is k, then ka is the answer to this expression here. Now what if we have this case situation where j runs from 3 to n and you have a? How do we work this out? And in some cases you might confuse this. I mean, usually this is not common, but I guess some of students do make mistakes in this case. They do this. They take away 3 from n and then times it by a as usual. If it were 1, it would be just n. But notice that what we're doing is here we are actually ignoring first two observations, or first two of the indexing operator, index numbers, and starting from the third. So we are actually ignoring 2, not 3 in this case. It's as if we're starting it from the fourth observation. So this is totally wrong. The correct formula for this is n minus the 3 here plus 1, because 3 is inclusive, times a. Now the answer to this expression will be 2n minus 2 times a. Right, and it's the same here actually. So n minus 1, that's this one, and that's n, plus 1 from the formula times a. So a is cancelled out. You have na, which is usually not mentioned in the books. Now let's look at the second rule of summation with constants. And let's say if you have this case where j runs from 1 to, let's say, some n, and you have a times x j, and notice a is not again indexed. In that case we could factor it out. Well, it will be put outside the summation sign. So that's the formula. Now what if we have a case where we have this situation, x j y I? Well, this summation operator is governed by j, not by I. So here we treat y as a constant. So this is being governed by some other operator probably that we don't know here. In that case, this would be out, and we have our xj here. Similarly, if you have these situations where the expression inside summation operator is a bit complicated, like something like this, plus 1. Well, what do we do here? Again, we are governed by j here, but we have xi. The whole thing is actually treated as constant in that case. So the answer is n times 2x j plus 1. Right? So these are basic rules. Now we have another rule called distributive rule. Let's clean this up. In the distributive rule, the third rule here, we might have a case such as this one here, where we sum xj and yj. Distributive rule says you can have the sums of x's separately from the sums of y's, right? So that's a very neat rule. I like this rule myself. It simplifies the proofs later you will come across. Now this applies to y, sorry, negative, so subtraction as well. So if you're subtracting, this plus minus should be there. And also, sorry for my sort of kind of handwriting. This is the first time I'm practicing with this pen tablet, sorry, that handwriting, and I hope it will get better over time. Okay, now let's look at some applications in econometrics or some statistics application. Let's clear this up. Now the first case you come across this summation operator is when you calculate the sample mean, where you don't denote it as x bar, and in that case x bar is sample mean is equal to sum of the observations starting from the first observation to the nth last observations divided by number of observations. And in some cases you will be using deviation rule, well, deviation from the mean rule. So let's say deviation, and it's usually sum of the deviations, I should say. Very often you will be using it for standard deviation calculations, xj minus x bar. So these are the two rules most often used in statistics and econometrics. Now let's take an example. One example is this. Let me clean this again. One example is this. Sum of the deviations of observations, sorry, yeah, sum of the deviations of observations is usually equal to 0. Now, well, it is, and you've done it before, and let's prove that it is actually equal to 0 using this summation operator, or we practice with it. And we know from the first distributive rule, let's say proof here, from the first distributive rule of summation operators is that we can have separate summation operators for each of these expressions. In that case, this would be j equal to 1, xj minus x bar. Oops, it's a bit too quick to write this, shouldn't be there, because I'm letting them to have their own summation operators. 1 to n x bar. Now this is interesting. Well, we can further simplify it by looking at this. I don't have much chance of simplifying it, so I'll just write it down to n xj minus. However, here if you look at this doesn't have an index here, and also this is an x bar, meaning at a mean, a sample mean, a number, a constant. It doesn't have sequence of observations, so it's a constant. So I could actually use the first rule of constant in summation operators. That means I'll times it by x, sorry, by n. So this would be n times x bar. Now we could do something else here. Let me write it down further. I'll keep the first expression as it is, minus. Now n, we don't have a chance to change it. Well, it doesn't change, it's a simple constant. However, we know that x bar from the previous example, which I cleared it now, this is equal to 1 over n, j equal to 1, n, xj. So this is actually the sample mean formula, isn't it? So I'll just, this whole thing is a sample mean formula. So I just wrote that formula here. Now there's further simplification here that needs to be done. And then you have xj minus, well, n's cancel out here, so you'll have xj's here. Well, that's 0 obviously, so these are the same expressions. So here we go. That's the proof that sum of deviations are 0, and I think in econometrics we will start with proofs in OLS where you have to prove that sum of squared residuals is equal to, estimate betas, beta 1, beta 0, the estimates betas basically, are uh, are estimated using estimates, that's quite often estimated using the rule that OLS uses the rule that the sum of squared residuals are a minimum. Or how to put this, I'll leave it to a later video where I'll have the appropriate word. I'm short words now to describe them in econometrics terms. So yeah, let's go to the next expression or next example where you will be using which you will be using in econometrics. And for this I'll just clear this video, sorry, the results. In econometrics you will come across this expression where j1 to n xj minus x bar squared, so this is the sum of squared residuals, is equal to j running from 1 to n xj times x j minus x bar. So, and this is an important simplification of these sum squared residuals, because this will be used in proofs and makes proofs easier to handle, I think. Now let's prove that this equation holds. So let's put proof. Now what is this expression? This expression is basically, let me rewrite it so that we know what we're doing. I can kind of open the square bracket while in the summation operator. While inside the operator I can open a square bracket. This would be xj squared minus 2xj times x bar plus x bar squared. Now we could, before we apply the distributive rule, well, we could use it now, but we can do a little bit more simplification here. J equal to 1 to n. Let's put the square bracket now. xj squared minus xj x bar minus xj x bar plus x bar squared square bracket. Now you probably noticed that this I just factored them into two expressions rather than one simple expression here. This allows us to put a bracket here and a bracket here, and then change this sign to minus. Let me do that now before it gets confused, in case you aren't following the video from the start. So this is now minus here because this is minus here once you close the bracket. When you open a bracket, it will become changed to plus sign. Now I think we can apply the summation operator to this expression and separately to this expression. So we'll have this result, j equal to 1 to n. First one now, squared minus xj x bar minus j equal to 1 to n xj x bar minus x bar squared. Right. Now I think we could do something here. There are xj's here, common factor in both expression here, and there is x bar is a common factor here. So I'll factor it out of the bracket here inside the summation operator. So, and now xj out of the bracket, xj minus x bar minus, here it would be j, and now x bar is out of the bracket here, xj x bar equal. Now notice that this is a constant here, so it can be put outside the, well, factored outside the summation operator. X bar is basically a sample mean, a number. So let's do that very quickly. Clean this. So I'm saving on time and space here. I'll just put the x bar here, and you'll know where this comes from already. So now what is this whole thing now inside this summation operator, xj minus x bar. This is deviation, yeah? Sum of deviations, right? And from the previous example, we know that this whole thing is equal to 0. Sum of the deviations is equal to 0. So that's implying something interesting here. xj, we cannot take this outside the bracket because it has a j index, so it got to be staying inside brackets, inside the summation operator. So x bar times, since this whole thing is 0, this is 0. Now we have proved that this sum of squared residuals, or sum of squared deviations I should say, not yet residuals, is equal to xj, sum of the xj's, yeah, xj minus x. So that's the proof, and this is very useful simplification of this expression, and will be useful in proofs when we have to do something with OLS exercises. So we'll do that at some point. Next, few other proofs, and then I think one more. We go to the next video then. Now we will have in OLS estimates, we'll have, well, exercise that involves proofs relating to OLS estimates. We'll have this sort of case where xi, well, xj I should use, because my I doesn't look nice. I don't know why, but I practiced it, it didn't work. And you have yj minus y bar. So that sort of expression here, this sort of expression is usually in statistics and econometrics proofs is equal to this expression here, j equal to 1 yj xj minus x bar, or alternatively, because there is a y and x variable, two distinctive variables, it could also be equal to this minus y bar. Now since my x looks decent than y, and I can write x better in this video, so let's prove that this expression equals this expression. So let's put proof. Now let's expand, open the brackets and expand this expression. I think that's the easiest starting point, I think. Let's multiply them out. So this would be xj yj minus xj times y bar, so xj times y bar minus this x bar times yj plus now x bar y bar y bar. Now you could actually move through the simplification here by letting the by rewriting this expression with summation operator separately for each expression here. But let's think of a way where we could manipulate this expression further, which allows us few omissions. Okay, let's look at them. Well, one thing I can think of is the same, using the factoring or splitting them into two expressions rather than into four, which then allows us to get rid of one of the simplified expressions. So let's do this. Let's get a bracket here and then bracket here. I think that this would help us to simplify it further, what it looks like. What does it look like now? So let's look at this. So in that case we'll have xj yj minus xj y bar plus, sorry, this is minus now when I put the bracket here, this would be negative, j equal to 1. Here we have x bar yj minus, because this after the bracket becomes minus, and well, something that can come out of the bracket here is 1 to n, let's say, well, let's put j for consistency, xj yj minus y bar. So this is a deviation of y, and xj is out of the bracket. That was common to both of these expressions. Now here we could take out x bar, then this will have yj minus y bar. And from before, oops, I shouldn't put equal to 0, I don't know why I did this. And then from before, we know that this x bar from the first rule of constant, second rule of constant comes out of the summation operator. So I could put it here, but for now we can leave it. And then what we'll have then is basically this whole thing will be x bar 1 to n yj minus y bar. This whole thing will be deviation sums, sum of the deviations, and we know that sum of the deviations is equal to 0, so that's 0. And then the result, well, I could write it here, is very easy. Now I can't do this here, this same simplification in this case, because x is indexed by j plus, sorry, this is minus 0 basically. So we now proved that this whole, well, not so beautifully looking expression boils down to a very simple expression here. If you want, you can go ahead and come up with, sorry, actually I tried to do this, but coming to this point here, I chose the easiest way of manipulating this, and then I ended up actually proving this point instead of this. Okay, so you can do this now. I think you can do this by taking the, well, I think if you change the bracketing here and keep putting together a few things here separately, you should be able to do that. I can see what it is, but I'll let you know now to do it. That ended funny, but I hope the videos are useful and will be helpful in your ECN 2 to 5 studies. See you in the next video.